Greetings and salutations and all those nice things. Hope everyone's doing well. In this lesson, we're kind of closing out this unit on applications of differentiation with an introduction to slope fields. Slope fields are some of the coolest things ever. And they're kind of, you've seen a magnetic field, for example, like iron filings or something. You've seen that kind of flow to those fields, and it's quite interesting to look at. So it has applications obviously very directly within physics, as much of calculus is built for. But slope fields are interesting things. We're only getting a little introduction to them right now. We are going to investigate them much more in depth later in the course. But right now, just a little feel for like, here's what a slope field is and here's how to plot one. And later on, when we get into like differential equations, we might then be talking about actually trying to find what equation gives us a particular slope field, and it's cool stuff. This right here is a blank slope field, so nothing in here is filled in yet. And it's a small grid, right? If these are all ones, then like that's 1, that's 2, that's 3, and -1, -2, -3. It's a pretty small grid for our purposes for filling out, just because to fill in a larger grid starts to get exponentially kind of out of control. So a pretty small grid. It could be larger if we wanted to be. If we wanted to go to 10, then we could go to 10. If not, then we don't. But it's just whatever's given to us, that's what we work with. And when we fill in a slope field, what happens is we are given an equation for the slope. So that slope, defined as dy dx, that has a definition. Maybe it's based on x, maybe it's based on y, maybe the slope is a constant, who knows? But we'll have some sort of equation for it. And what that will tell us is what the slope should be at every single one of these xy points. So where every single one of these points has coordinates, maybe it's at like 1, 1, or maybe it's at 3, 2, or maybe you're over here at -3, 0, so on and so forth. Every single one of these points has coordinates, and when we plug in those x and y values into the slope equation, we'll find out what that slope is at that particular point. We'll do that for basically all the points we can, and then that will give us, a look at what this slope field looks like. So over here, this is a slope field for dy dx is equal to x plus 1. So whenever we have any given point, we take the x and y values, and then in this side, we place in the x and y for whatever we see. 0, 0, we would have 0 plus 1, and the slope at that point would be 1. And if we check out the point 0, 0, we've drawn a little segment that has a slope of 1. So it's not like a full-on line. We're not drawing this like all the way across, but just a little segment at that one spot. Now, no matter what y value is, doesn't seem to make a difference on this particular one. This is just based entirely on x. So when x is 0 at all, and y is just whatever y value, this will always be 0 plus 1. That's why we see right up and down this axis where x is 0, we have all these little slope values of 1. When x is 1 instead, say we have the point 1 and any y value, the slope would be 1 plus 1, which is 2, which is why this whole column where x is 1, we have little slopes that are kind of about 2. Actually, I drew this pretty precisely, so those ones actually are pretty directly exactly 2. We might not be 100% accurate, but this field should give us a vibe if we were drawing it ourselves. So anyways, the slope field for dy dx is x plus 1. And we can actually kind of see a parabolic nature in this field where it's kind of got this archy flow to it. And that's probably because dy dx is linear, which then means that if we're looking at y itself, it's probably something quadratic, right? So because we know if we take the derivative of a quadratic equation, a quadratic function, we're going to get a linear function as its derivative. So that's why we can see that in there. So that one's based on dy dx being x plus 1. This other one is actually based on x and y. So x and y are both involved in here. If we want the slope when we have the point 1, 1, well then x is 1, y is 1, and that slope is 0. So at the point 1, 1, we have a little tick with a slope of 0. If we look at the point, 0, 1, well, then x is 0, y is 1, and x minus y, or x minus y is negative 1. So at the point 0, 1, we see a little slope of negative 1. And when we put all that together, and if we were to slowly fill out the entire thing, this is what we would see. So whole entire field coming together. What is this equation based on? Who knows? Who knows what y itself is, or how x and y are implicitly defined together. But this is the field when dy dx is x minus y. There are ways we can put it together with a little bit of efficiency. There are patterns that happen. One thing worth looking at is wherever the slope is 0. And we can take something like this and say, what if the slope is 0 and 0 is equal to x minus y? Well, that happens when y equals x, right? Just by adding y to both sides. So right along this whole line of y equals x, we have little slope marks of 0. We could also look at when the slope is undefined. That would give us vertical markers, but this is never undefined. For every x and y value, x minus y will always be defined. Undefined could happen when if we're dividing by 0, for example. Then we're going to have something that doesn't exist, or all has a vertical slope anyways. So there are things we can look for, and we can look for when the slope would be 1, when the slope would be negative 1, and use that to kind of help plot this whole thing out. And we'll see patterns kind of emerge, right? And this one, to the left of a 0 slope is a negative 1, and it looks like a negative 2, a negative 3, a negative 4, and it's slowly increasing in a negative direction that way, more and more sloped. And then on the other side, slope of 0, to the right of it, an increasing slope. Next one probably even be more increasing, and so on and so forth. So there are ways we can put things together with some ease, so it doesn't have to take 500 years to put it all in there. So we've got 2 whole egg samples. I might do this in pink. This is one of them. And again, you can just take this and start taking every single coordinate point and plugging it into this slope equation and using that. But it might also be helpful to just start by asking these questions, like where will dy dx equal 0? We'll figure that out by taking this dy dx and replacing it with 0. Oh, so whenever x is 0, dy dx is 0. X is 0 right along this y-axis. So along the y-axis, I'm going to fill in slopes of 0. Because dy dx, the slope, is 0. When will dy dx be undefined? Well, we're not ever dividing by any variable, so that's a straight up never. Where will dy dx be 1? Replacing dy dx with 1, it's wherever x is 1. Okay, since dy dx is the same as x, that makes sense. So whenever x is 1, we're going to have a slope of 1. So we draw little segments showing a slope of 1. where will dy dx be negative 1? Well, again, just replacing all the dy dx's with negative 1. We just have that. So it's whenever negative 1 is equal to x. So along the line x equals negative 1, we can fill in slopes, just like that. Take a moment, see if you can find out what the rest of this slope field looks like. Give it a try. Just draw it, see what happens. Take, 2 minutes and 45 seconds to give it a go. Pause the video and then resume. All right. Continuing this, I'm going to look at all this column. And I'm ignoring y values. Really, I'm just kind of focusing on x because dy dx is given to us just in terms of x, not in terms of y. When x is 2 over here, the slope is 2. So I'm going to draw slightly more sloped lines here. That might not be a perfect 2, and there are ways to actually make sure it's better than that, but actually you can imagine this being, what am I doing? Yeah, that. A line with slope of 2, right? Just, where's the green? Up 2 over 1, up 2 over 1, up 2 over 1. And that, taking that segment with a slope of 2 and drawing just a little piece of it, that's how you can get a pretty accurate version anyways. Similarly, when x is 3, the slope is 3. So going into this right side, getting even steeper. So we can see that slight change as we move further and further along. Similarly, on the left side, when x is negative 2, the slope dy dx is negative 2. So we draw little segments with slopes of negative 2. Oops, I'm starting to level off there. When I draw it, I'm essentially aiming for the one that's 2 down and 1 over. That's how I'm trying to maintain accuracy here. So same when I draw the slope of negative 3, I'm going to aim this dot towards that point 3 down and 1 to the right so that I can pretty much get the slope of negative 3. That. All right, so this gives us a vibe for this slope field. On the next page is another one, and that next page, other one, is based on x and y. So it's a little bit more involved, and certainly much more involved than just a simple x. But I super dare you to give it a try. It looks like this. It is a doozy. But go through these pieces, find where dy dx is equal to 0, find where it's undefined, and then start plugging in x, y points. Whatever point you want to find, if it's looking at this point, plug in that xy value into this slope equation and see what you get. But yeah, take like a solid 5 minutes right now and work with that, see what you get, and then resume the video. All right. I'm guessing that this video is running, otherwise you wouldn't be hearing the video's audio component. Anyways, where will dy dx equal 0? So we're wondering where 0 is equal to negative x plus y over y. Oops. That negative should be positioned differently. You could write something like this. The thing is, the only way to get a fraction to equal 0 is if the numerator equals 0. So we really don't need to look at that whole entire thing. This fraction will equal 0 when x plus y is equal to 0. You could also say negative of x plus y is equal to 0 to account for that negative there, but when you multiply both sides by negative 1, you're just going to get that anyways. So where does dy dx equal 0? And that's where y is equal to negative x, right? If I just take this x, move it to the other side. So along the line y equals negative x, we're going to have a slope of 0. The line y equals negative x is this line right here. So right along that entire line, I'm just going to draw tiny little slopes segments of 0. So 0 there, 0 there, 0 there, 0, 0. All along that line of, how do you say, y equals x, or y equals negative x. Actually, we will find out shortly. Maybe you've already found this out if you already drew your slope field, but one of those is erroneous. But where will dy dx be undefined? That's wherever we're dividing by 0. And the only thing that can make us divide by 0 is if y is 0. So dy dx will be undefined whenever y is 0, straight up. So undefined is going to give us a vertical slope whenever y is 0. And y is 0 along this axis, which is why this one segment is technically not true. We'd have to do a bit more work to figure out exactly what's happening there. But realistically, it's undefined. So we're going to include, what's an eraser when you need one? There. So there. So I'm just going to draw little vertical segments for that entire stretch. And now I'll check on the other things. Where will dy dx be 1? So that is when 1 is the slope. Dy dx is 1, so negative x plus y over y is equal to 1. Negative x plus y over y is equal to 1. And then we're just going to kind of solve this. Y equals negative x minus y. Applying that negative to the top. 2y is equal to negative x. So y is negative half x. So along the line y equals negative half x, we're going to have a slope of 1. The line y equals negative half x has an intercept at 0 and then a slope of negative half. So it's hitting these points as well and kind of cutting through there. And at those points, the slope will be 1. So I'm going to draw little line segments with a slope of 1 at each of those points. So a little line segment with a slope of 1. Not this middle one, because it's all sorts of wackadoodle. And this other one bottom right. That's got a slope of 1. And any other prompts here? Where will dy dx be negative 1? Okay. So negative 1 is equal to all that stuff. X plus y over y. You can multiply by y and by negative 1 at the same time, just since negatives are going to cancel out. Thus telling us y is equal to x plus y. Oh, that's interesting. Subtract y from both sides. 0 is equal to x. So wherever x is 0, dy dx, the slope is negative 1. X is 0 along this axis. And along that axis, then, the slope will be negative 1. So along that axis, drawing little slope segments of negative 1. Ignoring this zone, because again, it's a madhouse there. You don't want to go there. It's dangerous. The whole density of a black hole is swirling in right there. Well, the rest of this needs to be filled in. And it takes a bit of time. You can compute some of these things in your head if you want. But we're going to need to take all of these unfilled spots and plug them in. And I mean, you could do them on paper if you want, but it might be faster to just not. So like the 0.11. In my head, I'm going to take this numerator first, which is 1 plus 1, so that's 2. I'm going to divide it by the denominator. So 2 divided by 1 is 2. And then apply negative. So instead of positive 2, it's negative 2. So at this spot right here, drawing a slope of negative 2. And same here. We've got the 0.12, x plus y is 3. 3 divided by 2, because that's the y value, is 1.5. So we're looking at negative 1.5-ish. So slightly less sloped than that. This was a slope of 2. A slope of 3 would be much steeper. Slope of 1.5 is a little bit shallower. That's kind of if I was going down 3 over 2, right? Yeah. So taking this, I'm kind of aiming for that point over there. Oh, too much. This would be easier if I had a ruler. Yep. What you gonna do? This envelope will help. You can't see the envelope, but I swear it's there. Up here, that's the 0.13. X plus y is 4. X plus y divided by y is then 4/3. So we're looking at negative 4/3. 1, 2, 3, 4. So I'm kind of aiming for that spot when I draw this slope. I'm gonna put my envelope back on the screen here. Help me guide that. I'm basically just drawing a ruler, putting a ruler against those 2 points and then drawing the tiny line segment. Oopsie daisies, too far. So that's that. And again, now I've got to just kind of keep going. I'm probably not going to describe what I'm doing for the rest of them. I'm probably just going to fill them in. Is that what I'm going to do? Nope. Describe it. Might go faster. Who knows? All right. 2, 1. 2 plus 1 is 3. Divided by 1 is also 3. So we're looking at a slope of negative 3. Oh no, my ruler. That's an eraser. That's still an eraser. Nailed it. At this point, I could probably get some sort of pattern detection going here, because we went from a slope of 0 to negative 1 to negative 1.5. Negative 2 was it? Oh yeah, that was negative 2. Negative 3. Next one over is probably negative 4, if I were to guess. Yeah, straight up. And you will see kind of a linearity to these changes. Oh, filling it in. Yeah, I should get this whole thing. What's 2 plus 2 divided by 2? Oh, that's 2. So we need a slope of negative 2. Welcome to the most boring part of this video, listening to me do arithmetic. 3 plus 2 divided by 2. I need negative 5 over 2. 1, 2, 3, 4, 5. About there. That one's done. The 0.32, that's 5. Oh, I did this top one wrong. It should have been 5 over 3. That was my mistake. 2, 3. I think. Anyways, over here, that's negative 5 over 2. 1, 2, 3, 4. Am I even counting correctly? 1, 2, 3. Oh, that's why I drew this one wrong. Wow, this video is riveting. Hope you're having the time of your life with this thing. That looks slightly better. Back to this one. What was that? Negative 5 over 2. Got it. And then up top, 3 plus 3 divided by 3 is 2, so we're looking for a negative 2. Oh yeah, it's all coming together. Other points. Oh my gosh, this takes forever. I mean, I love it. This is the best. 3, negative 1, so x plus y is 2, divided by negative 1 is negative 2, and then multiplied by negative 1 is positive 2. So, that. Over here, 3 minus 2 is 1, divided by negative 2 is negative 1/2. This becomes positive 1/2. Over here, 1 minus 2 is negative 1, divided by 2, divided by negative 2 is 1/2 times negative 1. We're looking at negative 1/2 right there. Over here, 2 minus 3 is negative 1, divided by negative 3 is negative 1/3. So we're looking at positive, or somewhere along the line I messed up a negative. It's definitely negative 1/3 though. One minus, what's the number I'm going for here? 1 minus 3 is negative 2. So negative 2/3. And for me to, I'm just connecting it to that line here. That's where I'm drawing my envelope. Sorry, my ruler. I'm not using an envelope, but I am. Whew. All right, next biggest section to tackle. Negative 1 minus 1 is negative 2. Positive 2, negative 2. Nailed it. Negative 1 minus 2 is negative 3. So positive 3/2, negative 3/2. Negative 1 minus 3 is negative 2. So looking at negative... What the snot? What did I do in the last one? It's so easy to make all these little arithmetic errors. Negative 1 minus 2 is negative 1. Negative 1/2. Yeah. Yeah. Honestly, if you haven't like skipped ahead yet, yikes. You should probably just skip ahead to the answer. I mean, you can listen to me dictate what I'm doing this whole way through if you want, but oof. That sounds like a pain. But hey, it's your time, so follow your heart wherever it may lead. Negative 2 minus 1. Oh my gosh. Was I even doing this correctly? Yeah, I think so. Negative 2 minus 1 is negative 3. What's over here? Negative 3 minus 1 is negative 4. About there. Nice. Negative 2 minus 2 is negative 4. So we're looking at negative 2. Yeah, these look off. I probably added it instead of subtracting. Negative 1 minus 2. Negative 3 halves. Yeah. Negative 4 over 3. There. Negative 5 over 3. So about there. So connecting that line. Whew. All right, moving down. That's negative 5 over 2. Down here, negative 2. It is totally worth noting patterns that you might be seeing. Like, there are tons of ways to speed this up. I'm really just taking this whole process. But like, there's this negative 2 slope that happened along this particular path. And we could show that that happens just by like saying, hey, when will dy dx be negative 2? And see what we get. And you could do that for any particular slope you happen to find in your slope field as you're working through it. Just, it can make things faster. You don't have to. And I think it's still good to get a feel for actually plugging in the values here. Just for that measure of how it goes. All right, last 5 points. Negative 3 plus 1 is negative 2. What do I do with my life? Right, so it's positive 2. Over here, negative 3 plus 2 is negative 1. Divided by 2 is negative 1/2 times negative 1 is positive 1/2. So connecting to that one is what I'm going to do. Over here, negative 1 plus 2 is 1. Divided by 2 is 1/2 times negative 1. Negative 1/2, I'm going to connect it to that one. Or towards that one, I should say. I'm not actually connecting it, just drawing my short little segments. Over here, negative 2 plus 3. Negative 2 plus 3 is 1. Divided by 3 is 1/3. We're looking at negative 1/3. So I'm going to take this and draw it towards this zone right here. And over here, negative 1 plus 3 is 2. So looking at negative 2/3. I take this and try and connect it in that direction. Whew. And that is that slope field done. It was a doozy. But what a thing of beauty it is. Yeah, these slope fields can take a lot of time. So this practice work involves like a fair amount of kind of drawing slope fields. And we'll look at it more in depth later, but really get a feel for just where they come from, what they look like. If you want, just for fun, play around in Desmos. It's probably possible to enter this in the app too, but if you're just using a desktop computer or whatever, you can use a slope, like search Desmos slope field, as I did up here, and the first hit is slope field generator. Super cool thing. It defaults by putting dy dx is 2y over x in here, but you can put it to be other things, right? We just put it as negative of x plus y divided by y, and then that's the slope field we got. When you do that, it also has this little marker that you can drag around anywhere, and wherever you put it, it's going to try and draw the slope at that point. It's really having trouble right in the middle there, isn't it? But it will follow that everywhere. It's really cute. But you can put whatever equation you want in here just to see what it looks like. You want to see what happens if dy dx is equal to xy? Boom, that's what you get. You want to see if it's y over x? Boom, that's what you... Ooh, that's cool. Anyways, play around with it just for fun. See what kind of cool things you can draw. Really just for fun. Be mesmerized. Look at the beauty in the mathematics that's all around us. Anyways, that's all I've got. It's been most lovely. Tell everyone I say hello. Be good to yourselves and be good to one another. And believe in yourselves and believe in the dream.